This is a diagram of the electromagnetic spectrum. In the middle here is the very small amount of the spectrum that's visible to human eyesight, which runs from about 700 to 400 nanometers. If we look at this diagram, we can see that we are looking at wavelength here, which is measured from the top of the wave to the top of the next wave. How long is that wave, like if I stretched it out? And that is in meters, or oftentimes for visible light or smaller, it's in nanometers. It's important to look at the units and be sure that you are using something that will cancel correctly. And in our case, wavelength is increasing as we go towards the left. And you'll often see wavelength represented with the lowercase Greek letter lambda. So lambda is increasing to the right as we go across the screen. Wavelength is related to frequency. So if you take your hand and you make a long wave in front of you, just take your hand and go up and down in front of your face, you'll see that your hand is not going up and down all that many times with your long wave. If you make a very small wave, the wave is very frequently going up and down, up and down, up and down, up and down. So we find that frequency, which is denoted with the Greek letter nu, or sometimes just as F, is inversely proportional to lambda, or wavelength. So the longer your wave, the less frequently it's going to go up and down. The unit for frequency in this image is in hertz. Hertz is another way of stating inverse seconds to the -1, which of course if you've done your algebra is equivalent to 1 over seconds. And there is a relationship between frequency and wavelength that is very useful. It relates both to the speed of light, which is a constant, c. c is equal to lambda times nu, or lambda f. C is a constant. C is 3.0 times 10 to the 8th meters per second, because that's a speed. It is important to think about that because that is in meters. So when you do math with it, you need to make sure that your wavelength is also in meters, so this will cancel out. The other thing in this diagram is thinking about energy. And in our case, energy is increasing as we go to the left, which tells me that energy and wavelength are inversely proportional to each other. A very small wavelength, like our gamma rays, has a very high energy. And our very long wavelengths, like radio waves, have lower energy. And there's a relationship here that we can use, but let's think for a second. If energy is inversely proportional to wavelength, and frequency is inversely proportional to wavelength, then in fact our useful equation here relates energy directly to frequency using a constant. This h here stands for the Planck's constant. And h is equal to 6.626 times 10 to the negative 34 joule seconds. That's a very tiny number because it's looking at one photon or one wave of light. And one wave of light is not very much, so it doesn't have very much energy. So let's relate this to two kinds of problems. Just a straight, direct, light math, let's move around equations problems, and one that's a little more chemistry related. So here's just a straight, direct, light math problem. I've given the wavelength of light is 600 nanometers, and I want to know first what is the frequency of this light. Well, I know the equation that relates wavelength to frequency is C equals lambda nu, or lambda f. So I write it I solve it, I math it. So write it. Then if I put C over lambda, that would be equal to nu by itself, so I solved it. Now C is 3.0 times 10 to the 8th meters per second. And I would divide that by the wavelength. And this is where I see a lot of people make a mistake. They do this, especially if they don't remember to write their units, because when you write the units, you can see immediately you have an issue here. Nanometers and meters are not going to cancel. So let's not do that. That's a good way to get things wrong. We need to get our nanometers into meters. So let's take 600 nanometers, set up a little conversion factor here. And I know that 1 nanometer is 10 to the minus 9th meters. Nanometers on the top, cancel nanometers on the bottom. So this would be 600 times 10 to the minus 9 meters, which of course is horrible scientific notation. And if I were just going to plug this directly into a calculator, I might leave it that way because the calculator doesn't care if my scientific notation is pretty. But if I'm going to do it by hand, it's nicer to have it in better scientific notation. So that would be 6.00. And I made 600 smaller by 2 places, which means I add 2 to my exponent. -7 plus -9 plus 2 is -7. So I'll take 6.00 times 10 to the -7th meters. Meters on the top, cancel meters on the bottom. That puts this unit as 1 over seconds. Just because I canceled out the numerator does not magically put that seconds in the numerator. It stays in the bottom. So now if I look at this, I've got 3 divided by 6. 3 divided by 6 is equivalent to 0.5 times 10 to the, let's see, I'm going to take 8. Make this a little bigger and easier to read. 8 minus -7. Oh, minus a minus means plus. So that's 0.500 times 10 to the 15th inverse seconds. Let's make that nice scientific notation. 5.00. Since I made 5.00 to be bigger, I subtract. So I'll subtract 1 here. 10 to the 14th inverse seconds. And there's my frequency. If I want the energy then, well, I have an equation for energy. E is equal to HF. And that means I can just go ahead and do this directly because I want E. H is Planck's constant, 6.626 times 10 to the minus 34 joule seconds times 5.00 times 10 to the 14th inverse seconds. I see I have seconds times inverse seconds, so that's going to cancel. My unit then is in joules, which is good. That makes sense. So 6.626 times 5 is 33.13 times 10 to the -34 plus 14 would be -20 joules. Make that into good scientific notation. I do notice I have 3 sigdigs here, so we'll have 3 sigdigs in our answer. 3.31 times 10 to the minus 19 joules. So let's make something a little more chemistry related out of it. I have a problem here which gives me the ionization energy of aluminum in kilojoules per mole, and it would like me to find the longest wavelength with enough energy. Well, this would be hard except that I know, and now you know, that 1 photon or wave of light can interact with 1 atom. So I need to figure out how many joules I need per 1 atom. And then I can relate that energy to the wavelength. So let's do a little unit math first. 577.6 kilojoules per 1 mole. Okay, well, I don't want to be talking about one entire mole. I just want to be talking about an atom, and I know that 1.02 1 mole is equal to 6.02 times 10 to the 23rd atom. So now I can cancel out moles on the top and moles on the bottom. Now I'm in kilojoules per atom. But I do remember that the energy equation in Planck's constant is in joules. So I'd like to get out of kilojoules. 1 kilojoule is 1,000 joules, because I remember Planck's constant is in joules per second. So then I can take 577.6, divide it by Avogadro's number, 6.02 times 10 to the 23rd, and then multiply that answer by 1,000, and I get 9.595. 4 significant digits in my kilojoules per mole here, times 10 to the negative 19 joules. Let's make that look a little more like a 19. Okay, so now I know how much I need per atom here. Joule, we could call this, in fact, say joules per atom if we want. And I need to then think, how can I go from energy to wavelength? Well, the equation for energy is E equals HF. But if I think about it for a second, C is equal to lambda F. So I could solve this equation and get a lambda here. Lambda is equal to C divided by frequency. Well, let's see here. I could do this. I could get the frequency and I could plug it in later, but I could also notice that, I do have a relationship here that I could take advantage of. What if I solve for frequency? Frequency is C over lambda, but these frequencies are the same. So maybe I could just use this, where instead of using HF, I've used C over lambda because that's equal to F. If I write that, and then I'm going to solve that for lambda, because that's what I want, a wavelength that has that energy, that's going to be HC divided by E. And now I can go to the wavelength in one step instead of two. It doesn't really matter. You could get there easily in 2 steps or just 1. Just kind of depends on whether you like being a little more direct. H 6.626 times 10 to the negative 34 joule seconds. Okay, C, that's a constant, 3.0 times 10 to the 8th meters per second. And now I notice I have a second and a per second, so that will cancel out. Divide that by the energy, which I just calculated was 9.595 times 10 to the negative 19th joules. Now I have a joule on the top to cancel the joule on the bottom. And notice the only unit left here is in meters, which is great. That's what I would like. And so if I do this math, I end up with 2.072 times 10 to the minus 7th meters. And I could convert that into nanometers if I needed to, but it didn't ask. It just asked me for a wavelength. So a wavelength in meters, ought to be sufficient. Anything shorter than this will have enough energy. Anything longer than this will be lower energy and will not work. So this is the longest wavelength of light that has enough energy to ionize aluminum atoms.